Okay, so now we want to consider the situation where a object is accelerating. So no longer are we looking at objects that are at rest or at constant velocity. Here we have some objects that are accelerating. So we want to consider that situation. So our first example here, we have a block that is resting on the surface of an elevator, and that elevator is traveling downward and it's slowing down with an acceleration of a magnitude of 5 meters per second squared. So we definitely have some acceleration here, so let's look and see how we solve this sort of problem. Well, it's really the same process we did before. The first thing we do is we draw our free body diagram, right? So what are the forces acting on our block? Well, we've got our weight force here, so that's definitely acting, and then we have the normal force on the block by the surface of the elevator. So that's really it, right? We just have two forces, and so that means that we now want to jump to our second step, where the sum of the forces, so the sum of our forces, is equal to the mass times the acceleration. So in this case, it's not zero, right? There is some acceleration. So what is the acceleration? So the elevator is traveling downward, and it is slowing down. So its velocity is negative, and it's slowing down, so that means the acceleration is positive. So the acceleration is up here. So that means the mass is 2 kilograms. The acceleration is 5 meters per second squared. So that means the net force here, the sum of the forces, has to add up to be 10 newtons. Okay, so once we know that, now we do it the same way we did before. So the sum of the forces has to add up to be 10 newtons this time instead of 0. So our weight 1e force, so weight 1e, the mass is 2 kilograms, so that means the weight force is going to be negative 20, right? 2 times 10 is 20, and it's pointing down. Normal 1s, this force is unknown, we don't know what it is yet, and then we know that the sum of this has to equal the mass times acceleration, so that is 10 newtons. So at this point, negative 20 newtons plus the normal force is equal to 10 newtons, so we know that has to be 30 newtons. If we're doing it algebraically, negative 20 newtons plus normal 1s is equal to 10 newtons, and so then we would add 20 to both sides, so this becomes 30 newtons. Okay? So notice the thing that might cross people up is that they expect that the weight force to change. So the weight force is always going to be the same. What's going to change is the normal force. So how hard the surface is pushing against your feet. That's the force that's changing. And so maybe you notice this, right? So when you're riding in an elevator and as you're going down, so as it slows down, sort of you're pushed into the surface of the elevator, and so you feel heavier for a split second. So that's what's going on here. So the normal force that the elevator is applying to your feet is larger than your usual weight force, and so that means that you feel heavier for a split second. Okay, let's try a second question. So here we have a man who is 100 kilograms, and he is standing in an elevator that is accelerating downward at 2 meters per second squared. So pretty similar problem to the last one, except this time the acceleration is down, so our acceleration is going to be negative. So to do our process, let's do the free body diagram. So we have two forces here. We have the weight force pointing down, and we have the normal force pointing up. So, right, those are our only two forces, so we're good there. And so now the sum of these forces is equal to the mass times the acceleration. And so the mass is 100 kilograms. The acceleration, so the acceleration is downward at 2 meters per second, so that is negative 2 meters per second squared. So that means the net force here is 100 times negative 2, so that is negative 200 newtons. So the mass times acceleration, the sum of these forces has to be negative 200 newtons. Okay, so let's finish this off the way we did it before. Our weight force here, so the man is 100 kilograms, so times 10 is 1,000. So that means the weight force is pointing down, so it's negative 1,000 newtons. The normal 1s, we don't know the value of quite yet. Mass times acceleration, we just found. This is negative 200 newtons. So we need to solve for normal 1s. So we can do that. So negative 1,000 newtons plus normal 1s is equal to negative 200 newtons. So we add 1,000 to both sides, and normal 1s is equal to 800 newtons. So hopefully you see that, right? Negative 1,000 plus 800 gets you negative 200 newtons. So again, in this case, the normal force is lower than the one where the person is not accelerating. So that means that when you're standing in an elevator and it starts to move down, then there's a split second where you feel a little bit lighter because the elevator isn't pushing down on you. So it's same sort of concept, but in the reverse direction. All right, I think I have one more of these to do. So this is a tension question. I know this is on the homework, so we're going to go through this here. This is a little more complex, but it's really using the same concepts we've been using. So the idea here is that we have a fish that is yanked out of the water using a fishing line, and it breaks when the tension is 200 newtons. The string snaps, and the acceleration of the fish is 15 meters per second squared. And so now we want to solve for the mass of the fish. So this is a little different, but we set it up, we do it the same basic way. So to start it off, we want to draw our free body diagram. So we have the weight on the fish, and then we have pulling it up. This time we have the tension force. So tension 1R, so this is what's pulling our fish up, and then right at that moment it snaps, then that tension is equal to the 200 newtons. Okay, so that's step one. We've got our free body diagram. So in step two, the sum of the forces is equal to mass times acceleration. So this gets a little messier because this time we do not know the mass. What we know is that the acceleration is 15 meters per second squared, so that means it is 15 times the mass. Okay? So we don't know the mass, but we do know that whatever it is, it's 15 meters per second squared by the mass. So that means that our forces have to add up to be that value. So let's do our forces. So we've got tension 1R. So tension 1R is pointing up, and it is 200 newtons. And then the weight force here, again, we don't know exactly what it is, but we know that it is negative mg, so it's going to be negative 10 times the mass of our fish. So I'm just going to use m for our fish, for the mass of our fish here as a variable, and so that means that if we add these together, this is mass times acceleration, so this is going to add up to be 15 m. So in this case, I think we want to break this out into a formula, right? 200 newtons minus 10 times mass is equal to 15 times mass. So 200 newtons minus 10 m is equal to 15 m. So we're going to add 10 m to both sides. So 200 newtons is equal to 25 m. Then we divide both sides by 25. So that means 8 is equal to m. So that means our end answer here is that the mass of our fish here is 8 kilograms, and we did it the same way we did it before, just this time we didn't know the value of the mass, so we had to do a little bit of algebra to make sure that we could find that value. All right, so you have a few more questions to do, but I think this is a good place to stop. So you can imagine we can keep adding new forces and new complexity to this sort of question, but hopefully at least at this point you have a good idea on the general strategy for solving these problems. All right, good luck and take care of yourselves.